Hello everybody and welcome to NPTEL online certification course on cryogenic electronics for quantum computing. This is lecture number 3 and in this lecture we will be actually studying the Schrodinger wave equation. Now, so the outline of this course that we will introduce to you what is the Schrodinger wave equation and what is the origin of Schrodinger wave equation, look into its mathematical formulation, what is the physical meaning of wave function, which is quite an important sort of parameter in quantum world. We will look into maybe a couple of applications in the Schrodinger wave equation. Using Schrodinger wave equations, what are the applications? For example, particle in a well, potential well, finite and infinite potential well, and then look into the concept of probability density function. Now, first of all, let's look at the Schrodinger wave equation and what is its utility when you come to either cryogenics or at quantum results. Now, we have already seen in our previous 2 lectures that many of the experiments at very low dimensions could not be explained properly by classical physics or classical mechanics, right? And in those places where the dimensions of the devices are so small, so for example, electrons and protons, nuclei and so on and so forth, that explanation using classical mechanics was not possible. As an example, when you look into the Heisenberg's uncertainty principle, classical mechanics tells me that if you look at object in space and time, it is fixed and you can predict its position a priori in a very well manner, but quantum mechanics tells us that that is not true. There is always a probability of finding the particle, from where we get the concept of particle as a wave. And this was corroborated by equations such as the double slit experiment and diffraction experiments. Now, in 1926, around that period of time, the Schrodinger actually tried to provide a formulation or a solution using wave mechanics or the methodology of wave mechanics, which means that when a particle is moving in free space or in a bounded space, a subatomic particle, how will its behavior be known if we apply wave associated with that particle as one of the parameters for extraction. So that was in 1926, Schrodinger tried to provide a formulation for that, and it was incorporated using Planck's principle of quanta and de Broglie wave particle duality principle. Now, de Broglie said that of course that wave and particle are dual with respect to each other, and wave being in quantum world and particle being in classical world, and all these 3 mechanisms together, which was basically the Planck's photoelectric effect showing that the light is in form of quanta rather than wave, and double slit experiments showing the diffraction pattern and interference pattern showing that the electron also starts to behave like a wave, right? So these experiments gave the concept of duality within the quantum mechanical world. Now, as I discussed with you, we'll come to that first equation, and that is known as the Schrodinger wave equation, which is given by this. Don't be too much perturbed by the equation itself. It looks complicated, but it's really easy to understand and easy to do it if proper understanding is there. Now, this equation which is blocked here is known as a Schrodinger equation, and it's basically in this case happens to be a differential equation, right? And it has got 2 dimensions, one in terms of x, another in terms of t. X and t are the position and time respectively. So I will come to that later on. X is position of the particle with respect to any point, and t is the time with respect to the action. So when the action is done at t equals to 0, let us suppose the particle has moved by a certain distance, its associated wave will be also shifted in time domain, and that's what you are differentiating on the right hand side. And therefore, it, as I discussed with you, it describes the wave behavior through wave functions. Now, out of which, if you look very carefully, the psi of xt is the wave function. At this stage, please keep this in mind that this is basically a formalism of the wave which gives you the probability of finding the particle between the absence and presence of wave. So if there's a wave which is something like this, then we are trying to find out the probability of the finding particle between these 2 points will be always equals to 1, right? And we'll see to that later on how it works out. So there are 2 forms of Schrodinger wave equation. The first one is time dependent and the second one is time independent Schrodinger wave equation. So what you see here in this slide is basically time dependent Schrodinger wave equation. When time is not part of this differential equation, only one dimensional Schrodinger wave equation is there, which is space dependent. That is defined as the space dependent or simply time independent Schrodinger wave equation. And two things therefore, this equation in a sense, if you are able to solve it under certain boundary conditions, then this equation will help us to understand how does the wave function vary with respect to x and how does the wave function vary with respect to time, right? That these two aspects are there. And therefore, if you can predict a priori the position and the time of the wave function, you can also therefore predict what is the probability of finding the electron within the space and time domain. So this is the one dimensional, also referred to as non-relativistic. I will not use that term, it will make you less confusing. We will assume this to be as a one dimensional Schrodinger wave equation, which is given by this formula. Why one dimensional? Because in space it is only differentiating with respect to x. Now let's take up each term of the Schrodinger wave equation and explain to you what these terms are. M is the mass of the particle, right? So the mass of the subatomic particle which is there is m. Psi of xt is basically the wave function, and this is the most important sort of parameter which helps you to predict the presence or absence of a particle. This v is the potential function. For example, if I have an electron moving in a free space where there is electric field presence, electric field will imply that there will be always a rate of change of potential with respect to x. dvx dx, this will give you the value of ex. Ex basically means the electric field in x direction. That is given by Vx. So I am assuming that the potential is x dependent. It might also happen that there is no dependency of V on x, right? So it's a constant potential which is being applied and it is independent of the space. Then we will remove this term x from here and we will have a constant potential. This we multiply with wave function psi xt, and that must be equals to j h cut del psi x del x del t, right? Where h cut is basically, you know already what is h cut, is h by 2 pi modified Planck's constant. J is a complex number, denotation of complex number, and it is given by square root of -1, right? H cut is already known to you, and psi t is the wave function which you see. So on the left hand side you have space dependency, on the right hand side you have time dependency. So this gives you a brief idea about the one dimensional Schrodinger wave equation which is there. Now let's come to the physical meaning of wave function. Now if you look at this physical meaning, basically it gives me a comprehensive description of the quantum system, right? So if you are able to predict the value of the psi xt, and if I can show you it as a function of space and time, then I can predict a priori the various parameters in a quantum system. So I will give an example. Let us suppose I have an electron which is moving across a crystal lattice. So if I have a crystal lattice, I can show it by these lattice points here, right? Lattice points. Now if electron is moving like in this manner, then you will see that the potential will become extremely low at the point where you will have these lattice. This lattice will give you these extremely low points, and the reason is, since the lattice is stable, here the energy, so this is basically my V of x, and V of x becomes almost very low at the point where the particle is stationed. This basically means that it's basically a stationary and a stable particle is available. So now when an electron moves across this network, it actually sees such variation in the potential from point A to point B, right? And therefore this potential variation is there. So what will happen is that this will influence the wave function, and the wave function will change for this particle, and therefore the probability of finding the particle in the space will vary as you move from one point to another. Now the way people solve it in most of the cases, the Schrodinger wave equation, it's basically a partial differential equation, and therefore you require a set of boundary conditions, right? Now these boundary conditions comes from the actual problem in hand, right? So for example, I will tell you in this case, if you take this as a set, then I can say that, let us suppose this is L, this is L, this is also L, the distance between the two lattice points, and this is effectively L by 2. Then at minus L by 2 and plus L by 2 here, the potential is maximum, and exactly at 0 the potential is 0. So this will define a sort of boundary condition for the psi xt. So what people do generally is, researchers over a period of time, they segregate psi xt into two parts. One is space dependent, another is time dependent. So psi of x, right? Sorry, this should be psi of x is the position dependent part of the wave function and is time independent part of the wave function. So it's space dependent, whereas phi of t is the time dependent part of the wave function, right? So psi of x is space dependent and psi of t. Take this value from here, right, and take this value of psi xt from here, and then what you do is you go back to the previous case and insert the value at this point, at this point, and at this point, then differentiate it. Then what you do is that you give a sort of generic wave function for psi x and psi t, and then start doing the equation, put the boundary condition, and finally you will get an equation which will relate the potential with respect to psi of xt. Now, psi of xt is basically a complex valued function. I am not doing it rigorous analysis here because there is a limitation of time, that the square of the magnitude of this quantity gives you the probability density of finding a particle in a given position and time, which means that if I know psi of xt, I just need to square it, which means I just need to square it like this, multiply by itself, and the equation which you get, or you get totally the probability function, psi of xt, probability density function. This probability density function is obviously again depending on the x and t value, but then you do have now therefore an analytical expression wherein x and t are variables, and therefore just fitting the value of x and t, you will know what is the probability of finding the particle in a particular position and time within the space and within the boundary conditions of the problem which is in hand, right? Now, there is another way of writing psi xt, is that you write psi xt into multiplied by its complex conjugate. So when you multiply its complex conjugate, the real function stays with you, and therefore you will be able to extract the value of pxt. So the way we generally do it in quantum mechanics is that we multiply psi xt with respect to psi of star, complex conjugate. So you multiply the function with its complex conjugate, and when you multiply with complex conjugate, you get a real function which is a probability density function in sense. Now, this I have already told you, but let me give you an idea. So let us suppose I have an electron flowing in a space, right? So therefore, if you look at this equation, right, now psi of xt square is basically the probability of finding the particle. So if you look at this particular point, then it basically means that between x and x plus dx, right, sorry, x and x plus dx, what is the probability of finding the particle is given by this expression. But however, if you integrate it from minus infinity to plus infinity, the probability function will always come out to be 1. Why? Because you know the particle is there in a region which does not have any potential function, but you are very sure that the particle will exist between the boundary conditions set, and therefore the probability is always equals to 1, which means that, let us suppose it's something like this: you are standing in a room, the room might be as big as you want, but if you take the boundary conditions as the edge of the room, and if I want to find out the probability, I am 100% sure that I will find you within that room itself, and that's the reason the probability is always equals to 1. However, in order to solve these equations, two important, not boundary conditions, but two important conditions of wave function is required. The first is that psi x should be finite, right? It should be finite, and it should be single valued and continuous. What do I mean by continuous? I will tell one by one. Why finite and single valued? Because if it is infinite, then if I multiply psi with psi of star, it will shoot there, and therefore I can very well say that at any particular point in the space the probability is almost close to 1. Then you will be violating the Heisenberg uncertainty principle, and that's the reason it should be finite. It cannot be infinite, but it should also be single valued. The reason it cannot be a multiple value is, therefore, if it is a multiple valued, then within the same space a single electron's probability of finding is at point x1 and x2, 2 points. Again, not possible, because a particle exists only at one of the points, right? And that's the reason it should be single valued. It should be continuous. Continuous primarily means that the value of psi at x, right, if you approach from the left of x, and if you approach from the right of x, and if you are approaching at x, all the three values should be equal to each other. Then we define this to be as a continuous function. If there is a discontinuity, then you will never be able to find its complex conjugate, and similarly you won't be able to find the integral from minus infinity to plus infinity. And that's the reason the wave function should be single, it should be finite value, continuous. Similarly, the first derivative of psi x should also be finite, single valued and continuous. First derivative basically means it is psi of d psi dx, also referred to as psi prime of x, right? This should be single, continuous and single valued, finite and continuous. Why? Because d psi del of psi of x gives me a how does the wave function vary with respect to x. If there is a discontinuity there, so there might be a reason where there is a sudden increase in the value of psi x, right? And it is becoming infinite at a particular point. That will result in non-continuous waveform for d psi dx. Again, not acceptable. So these are the two boundary conditions for the wave functions which we apply. So we have understood the basic concept of wave function, right? What is the Schrodinger wave equation? Time independent, time dependent. We also looked into what is the meaning of wave function, the mass of the particle relation, and how this wave function is a space and time dependent. We also saw that to find the probability density function, we need to multiply the wave function with its complex conjugate. With this knowledge, and also the last one was that psi should be finite, single valued and continuous. Similarly, d psi dx should also be finite, single valued and continuous. If these are not met, the very tenets of quantum mechanics will be lost, right? So with this background, let's take up a study case, right? Study case is that let's take up a potential energy function which is finite for all the regions and goes to 0 between x equals to 0 and x equals to a. So we are taking this discussion from Niemann book, right? You can also have a look in this Niemann book. Its ebook is available and its hard copy is also available in libraries and various places. And there in the first few early chapters you will find this discussion. This tells me that at x equals to 0, between x equals to 0 and x equals to a, the value of Vx, which is the potential applied, is actually equals to 0, and beyond x equals to a, this Vx value goes to V0, and less than when you go to x0, you will get Vx equals to V0. So it's basically a potential well problem which you see. So I have a potential well which is happening, right? This is the potential well. Now, if this discussion would have been in the classical world, if this discussion would have been there, then I would have been 100% sure that the particle would be somewhere in the middle of this potential well. Why? Because the first tenet of any stable system is that its energy should be as low as possible. So yes, so this energy is approximately equals to 0 and potential energy, and therefore it will have some kinetic energy, it will be feeding inside this region very well and will remain stable. However, as I discussed with you earlier also, that quantum mechanics does not allow you to do that, and therefore there will be a finite value of psi x even beyond x equals to a and x equals to 0. And that's what is shown here. So obviously this is high, so the probability of finding the particle within this region is also high, but you do have still finite probability just near the potential well, and it goes very fast, exponentially fast near x equals to 0 and x equals to a, which means that the probability goes down very fast as you move away from these x equals to a and x equals to 0 to further towards the end, because the potential has risen to a high value. Okay, so this is the finite potential well problem. Now let's take up like this, that this case study number 2, and we say that okay, in the previous case the potential was at x equals to, at V0 the potential was locked at V0 beyond x equals to 0 and x equals to a. What we have done here is, so the boundary still remains at x equals to 0 and x equals to a, but the potential well has gone to infinity, which means that there is an infinite potential well which is available. An example for that will be, say for example, you have a nucleus, right? The nucleus is a very, very strong attractive pull over electron. That will behave in such a manner that till a point where the potential is approximately equals to 0, you will get a straight line like this, and beyond that point it will be very difficult for the electron to leave that site. So the energy required for the electron to leave that nuclei will be infinitely large, and that's the reason you can see that they are almost at very, very high values which you see here. Now if you look at the potential equation now, psi x, it almost goes to, suddenly goes to 0 at these two edges, right? It goes to 0, at the middle it goes to a high value, which means that now the probability of particle being found within that gap will be relatively high. Now, so these are the two basic equations, and let me now solve maybe a basic Schrodinger wave equation and show to you how is it solved. So what we are solving is that electron is moving freely in a space, right? So there is no force acting on the electron, right? And there is a constant potential Vx available to me, and the total energy E is much larger as compared to the constant potential Vx. So if I assume that Vx equals to 0 everywhere, and if I want to do a time independent wave equation, then I get d2 psi dx2 plus 2 me by h cut square into psi x equals to 0, almost like a Laplace equation. The solution for that equation is given by this. Quite interestingly, if you see, this psi x is an exponentially positive function with a, and it's an exponentially negative function with respect to b, right? Which means that I'll just show you an example here. Just look at these two expressions here. But these are standard solution from mathematics. Now, if with increasing x, you only take the first expression, which is a exponential j of kx, then it will imply that psi of x will be finite, agreed. It will be again single valued, that also true, but it will be increasing continuously as you move your x to a high value. You get my point? And therefore, the violation will be that psi x will become very large, and therefore its probability will be high, and you will be able to predict therefore with certainty the position of an electron with respect to x, which will be direct violation of the Heisenberg uncertainty principle. So if you want to solve it intuitively, it means a equals to 0. If you remove a equals to 0, primarily meaning this to be true, then I have an exponentially falling function that suits our purposes. K is the wave number and is given as 2me by h cut square root of 2me by h cut. Now let's look at the time dependent part of the solution. I get phi t equals to exponential minus j omega t. We will not go into further details of this. Now if you do a complete solution, I get psi of xt equals to a exponential j kx minus omega t and minus kx plus b omega t six. And if your basic theory is correct, then this basically represents a traveling wave, which means that it is almost like behaving like so as a traveling wave. Traveling wave means a wave which is moving with respect to x and t within a free space where the potential is constant. You can also have a stationary wave. How a stationary wave is formed? That if I have a rebounding surface here, which is high energy surface, and the wave function and strikes here, and it returns back with a 180-degree phase shift, then this formulates what is known as a stationary wave. Stationary wave will have its own characteristics as well. Now the first term of this expression, so I get the value of psi t, the wave function, to be this much. So the first term with coefficient a, which is this one, with coefficient a, is a wave which is moving in the positive x direction, and the second term is basically the one which is moving in the negative x direction. Now the coefficients a and b are now determined by these equations, that if I imagine that the wave is traveling only in the positive direction, there is no negative wave, then b has to be equals to 0, because b represents a negative direction wave. So with b equals to 0, I end up having psi of xt to be equals to a exponential j of kx minus omega t, right? And where k is given as wave number, 2me by h cut, and this is 2me is nothing but p is the momentum of the particle, and is given as 2m times e is the energy of the particle. Now therefore I get the de Broglie corresponding wavelength is equal to h by p. Now as the value of p increases, if the e value increases, p value increases, this implies my de Broglie wavelength starts to go down, and therefore the lambda value will go down when you have an excessively large energy being inserted, and the wave is only traveling in the positive x direction, there is no return wave coming, and therefore the b value is equals to 0, right? So this is the way you solve generally the idea. Now what you need to find out is you need to find out the probability density function. So how will you do that? Very straightforward and simple. You do this, take its complex conjugate, it will be minus, they will cancel out with each other, and what you will be left with will be basically a square. So depending on the value of a, I can predict the value of the probability density function, right? And that will give you the probability of finding the particle within minus infinity to plus infinity. Therefore, and that last statement is quite important, therefore if a free particle with a known momentum and therefore known energy can be found anywhere with equal probability, and therefore that is consistent with the Heisenberg uncertainty principle, which states that precise momentum means an undefined position, and that's true also. So if I am able to predict the momentum precisely at all the points within the space, I will not be able to predict the position associated with. And that's the reason it shows an equal valued function across various values of x. Okay. So with this, let me stop here today. And we have learned about the basic Schrodinger wave equation, the concept of psi of xt, how is it related. Then gave you an idea about two case studies of finite potential well and an infinite potential well. We also understood what is the property of psi of xt should be and d psi of dxt should be there. Then we solved a Schrodinger wave equation, and after that we came to a point where we were actually able to predict the value of the probability density function with respect to the empirical constants associated with the solution of the wave function. With this, let me stop here today, and thank you for your patient hearing.